Hi, my name is Naya Wu, and today we'll be looking at Lab 3 Magnetic Field of Permanent Dipole Magnets for Physics 2212. The purpose of this lab is to further our understandings of bar magnetics and permanent magnetic dipoles. By doing so, we can first look at the correlation between the magnetic and the observable distance, both on and off axis. We will also take a look at the Biot-Savart law, which explains the relationship between the magnetic field and its displacement and magnetic dipole moment. And finally, we'll be computationally modeling the magnetic field. The result of this lab includes n equaling to negative 2.019 and the magnetic dipole moment to 2.24 ampere meter square. So for some concepts and formulas, we need to take a look at two formulas, the distance dependence formula and the Biot-Savart law, as you can see here. We also have to take into account the magnetic field of the Earth, especially for our Y value. Before we go on with the procedure, we first have to calibrate the phone and to see where our sensor is on the phone. So you have to download an app and calibrate it basically. To calibrate, we first put the phone perpendicular to the meter stick and find where the X component is max, the Y component is min. And then we put a tape on top to like label where it is. Afterwards, we will switch it and do the same thing, except for now the X component will be the min and the Y component will be the max. And you'll put the tape on vertically to the phone, and where the X meets up, that's where the sensor is. Okay, so with the actual experiment, what we end up doing is we move the phone around until the magnetic field, the X component of the magnetic field, is around 20 microteslas. You do this 3 times, find the average, and then you do the same thing again with other varying magnetic fields. And by doing so, we can find this graph right here, which is going to help us calculate the magnetic dipole moment. As you can see here, we have our combination of the two equations, and we first need to find K. So we do end up finding K using the data we have. So it ends up being 4.48 times 10 to the negative 7. You plug this in, and you get that the magnetic dipole moment is 2.24 ampere meter square. So for the code, we have some basics such as the magnetic field function right here. We also have our observable locations, 2 of them on axis, 4 of them perpendicular to the axis. Afterwards, we have the arrows that represent our observable locations. So we have some that are going to be orange, and the next one, some of they're going to be cyan. Lastly, we need to draw an arrow for the perp and the observable location 45 degrees away from the origin, and that's what we have here. At the end, it creates this. As you can see, we have our arrows, and we have this tiny little arrow in the back, which represents our 45 degree. Yeah, so that's it. We also did some measurements for the off axis, and as you can tell, compared to the data we see from Excel, and this is the data we see from the computational model, the X component is very similar, but everything else is a little bit off. Reflection questions. What if you haven't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick to some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? Well, the X component of the magnetic field wouldn't have started at 0 teslas due to the interference of the Earth's magnetic field. We wouldn't be able to tell if the sensor is being affected by the bar's magnetic field or the Earth's magnetic field. What if you were to stick two identical magnets together end to end, run the experiment again? How would you expect your measurements to differ? Well, the magnitude of the magnetic field would increase. Not sure it would double, but it would definitely increase. And that is all. Thank you.